chance to eat something. Welcome to Computex, welcome to our annual press event here. Without further ado, I'd like to hand over to you our CEO and founder, Jensen. Two more, and then we can start. All right. Guys, welcome. Let's see. Computex 2018. This is our press conference. Last week, we had our GTC 2018. Last year's GTC became the largest computer developers conference in the world, I think. 25,000 attendees all over the world. We kicked it off this year with record attendees in Santa Clara. This is our first stop outside of Santa Clara in Taiwan, but it's going to be a world tour. We'll go to Japan, we'll go to Europe, we'll go to China, we're going to go to Israel, we'll go to Washington, D.C. We're going to take GTC, GPU Developers Conference, all over the world. The reason for that is this. The new era of computing is in full steam. We all know now that the future of computing is going to be very different. And so I'm going to get right into it. I'm going to talk about basically four things. The first thing I want to talk about is give you an update on GeForce, the driving force of GPU technology. In no market in the history of technology have we ever seen technology demand for the processor continue to grow at exponential rates for over 2 decades while the market continues to expand. I want to talk about the second thing, which is AI computing. And then I want to talk about third, which is the implications of AI. And then fourth, a brand new market that we're pursuing. So let's get started. GeForce. As you guys know, GeForce is the world's largest gaming platform. The world's largest gaming platform started in desktops. It requires a great deal of computational horsepower, and therefore, the form factor of the computer is not insignificant either. Several years ago, we started working on a method to take GPUs into a very, very thin form factor so that we can all have our game console, game platform with us at all times. We invented Max-Q. Max-Q is pretty amazing. Matt, you could show me. Max-Q is pretty amazing. This is what a gaming notebook used to look like just a couple of years ago. Okay, this is a gaming notebook with a GTX 980 inside. This would be considered a portable. It's not quite a notebook PC. It's kind of a portable PC. You can port it around. In fact, people actually build backpacks that are designed for these computers. And so we invented Max-Q. This is the future of notebook gaming. From a portable notebook, portable gaming notebook, to a consumer, thin, beautiful notebook, still powered by GeForce GTX. Max-Q operates at a super energy efficient level, high performance, but battery conserving. And as a result, we're able to create a notebook that is thin and beautiful and yet powerful. Very heavy. I'm kind of winded now. I'm going to have to sit down. If I could have one of your cookies. Yeah, I got it. So, portable gaming, notebook gaming GeForce PC. This is the brand new MSI notebook. And it's really quite amazing. Look at this. 51 millimeters, 10 pounds, 17.7 millimeters, 4 pounds. And this is 3 times the performance of a PlayStation 4. 3 times the performance of a PlayStation 4. And you could also use it for Excel. And so, the future of notebook gaming. The amazing thing, of course, is so that we could create a notebook that gamers could use all the time and still be their favorite notebook. However, it also expands the market tremendously. Because the market wants thin, wants light, wants beautiful notebooks, we can now address a much larger market. And all of our partners here in Taiwan recognize that. 1 year ago at this time, we had 8 Max-Q notebooks. Today, we have 26 Max-Q notebooks going to market. The consumer notebook market is 100 million units per year. We can now address a much, much larger segment. Okay? So the first part, Max-Q. Great notebook, great gaming notebook, completely reinvents how gaming can be enjoyed, and also for all of our partners all over the world, allows us to enjoy much, much larger market opportunity. And also, it'd be great to have some oxygen now. Do I have some water? Wow, this job is rigorous. Throwing out cookies, lugging 10 pounds of notebook. Okay, Max-Q notebooks. PC gaming is really doing great. It is incredibly vibrant. Because it's an open platform, there are always new things that you could do with it. Because it's a powerful platform, content and great content continues to get richer and richer. And it's always reshaping itself. It's always reinventing itself. And so this last year is no different. In fact, if you take a look at this last year, in just 8 months, the PC gaming marketplace really took off. And it took off because a brand new genre was invented. Literally 8 months ago, Battle Royale came onto the scene. Battle Royale came onto the scene 8 months ago. And almost instantaneously it took off. Between PUBG and Fortnite, the number of active GeForce gamers, increased by 10 million gamers in 8 months. Now 10 million is a lot of people. 10 million gamers in just 8 months. The second factor, the second phenomenon that's happening is that the production value of games are continuing to increase. And it happens because, of course, consumers have greater expectation. The market size for gaming is now larger than ever. And so as a developer, you can invest a lot more to create amazing content. If you create the next Call of Duty Black Ops 4, you could be pretty assured that it's going to be a multi-hundred million franchise overnight. And so as a result, your courage for investing a great deal of R&D to make the content as rich as possible is increased. Also, game consoles creates a positive feedback system. Because for the first time, game console technology is actually very powerful. And so therefore, developers can have an even larger install base, larger footprint to go and invest great content. And so all of that is driving the adoption of higher-end and higher-end GPUs. In fact, if you look at it, this is truly amazing. In just 5 years time, our GTX class GPUs, X50 class GPUs, increased by a factor and above. Went from 17% of our overall market to over 50% of our overall market, growing at 50% per year. So basically what that says is that the high-end GPUs are growing faster than ever. And the reason for that is, of course, great content. So PUBG and Fortnite Battle Royale increased the number of users. Great content is increasing the adoption of higher-end GPUs. We create Max-Q so that we could put these high-end GPUs into these amazing notebooks and continue to expand the GeForce market. This fall, we're going to see 3 amazing games come out. Call of Duty Black Ops 4. Not only is it a huge franchise, as you guys know, it's also going to be the first time they include Battle Royale mode. I can't wait to see what that looks like. We're going to see also Battlefield 5 and then Shadows Tomb Raider. 3 amazing franchises are going to hit the market about the same time this fall. So I think this year is going to be a pretty amazing year for GeForce. You guys said this is going to get edited, right? So during my water moments, could you just cut it off? I had to feed 150 people earlier. So when I was a kid, I was a busboy and a waiter. But I never had to feed 150 people before. So that was really good. Cheryl, you did say this is not being streamed, right?
Yeah, that's right.
It's not being streamed.
Other people might.
They might be streaming. Okay, you guys, cut it short, okay? All right, the force is strong with this one. The force is strong with this one. All right. There's a new era in computing. Two very powerful forces are happening at the same time that's causing the future of computers to change. The computer architecture has to change. How we develop software has to change. How computers are made has to change. However, how software will be used will be incredible. The two dynamics are this. The first is that we know very well that CPU performance that used to scale over the course of the last 35 years has come to an end. In 35 years, CPU performance increased in performance by 100,000 times. And several years ago, it plateaued and it stopped growing. Well, unfortunately, the applications, there's more demand for computing horsepower than ever before. Scientific computing, whether simulation, discovery of new drugs, or this new application called deep learning and artificial intelligence came into the scene. These applications demand more computational horsepower than ever. Artificial intelligence is relatively easy to understand. It's very hard to do, but it's easy to understand because we are all intelligent and we're trying to figure out how to get a computer to be able to learn, to be able to adapt, to be able to improve, and most importantly, in the field of computer science, software is going to write software. A computer is going to learn, is going to be able to learn by itself from its environment, and software will write software. So the question is, what kind of computer do you have to build to allow software to write software? In order to write software, you're going to need supercomputers and very high-performance computers in order for the algorithm to learn from all the data that we're going to feed it and to write software that no human can write. So in no time in history do we need more computing horsepower at exactly the time when CPU performance has slowed. In fact, if you were to just extrapolate the implication from here out to another 10 years from now, to 2030 or so, we are expecting application demand to increase over 1,000 times. However, if we don't continue to accelerate and continue to advance computing, that gap is going to get larger and larger. Fortunately, we have a path forward. We call it GPU computing. We've been working on it for over 10 years, and the market has really jumped on top of this computing platform. Today, I'm going to talk about three things. I'm going to talk about the three stages or the three phases of this new computing model, particularly as it relates to artificial intelligence. The first phase of artificial intelligence is for the industry to create the fundamental computing platform, the architecture, the software tools, the methodology for developing this new type of software, and to create an ecosystem, an industry, to take these systems all over the world. That's phase one. Phase one is about creating the computing platform. And so as you can see, over the last 10 years, we have been advancing this new form of computing we call GPU computing. Recently at GTC, we announced the single most powerful single-node computer that has ever been created. This computer, called the DGX2, has 16 brand new processors. This is the Volta GPU. This is a reinvented GPU. This GPU is the first GPU in the world that fuses two styles of computing. Computational approach, the scientific approach, mathematics, with very high precision numerics, FP32, FP64, as well as a second type of computing that was recently discovered called deep learning. Deep learning requires a multi-mode computation approach, FP32, FP16, and even 8-bit energy, because it's able to compute at a very large dynamic range. However, it wants to have very, very high throughput linear algebra. We call it the tensor core architecture. So Volta, Tesla V100, this is one I'm holding right here. Volta is 21 billion transistors made out of 12 nanometer FinFET, 3D packaging, and lately we introduced the largest GPU that the world's ever made, 32 gigabytes of high-speed memory. It fuses two styles of computing, as I mentioned, high-performance computing as well as tensor core processing. 125 teraflops of tensor core performance, deep learning performance in this one chip. Inside this box, which is illustrated here, are 16 GPUs. Now these 16 GPUs allows us to do computing, parallel computing in two ways. One way is to have a model fit inside the GPU, and each one of the GPUs has different data that processes. It's called data parallelism. Same model on every GPU, and different amounts of data, parallel data, goes through the GPUs for processing. Another way that the high-performance computer industry calls it, it's called scale-out. The second approach is extremely difficult to do. It's called scale-up. Scale-up says, take a model, a very, very large model, and break it up into small pieces that runs in each of the 16 processors. 16 processors are going to team up together to do one computing simulation. That's called model parallelism. Model parallelism requires all of the 16 GPUs to be able to communicate with each other. It also requires that the software programmer is able to think about this large computer system at one time. We created a very unique architecture with DGX2. For the very first time, all 16 of the all 16 of the GPUs inside the DGX2 can communicate to each other all at the same time. Everybody can talk to everybody at exactly the same time. The programming model is also exactly the same, programming 16 GPUs as it is programming one. As a result, we created the world's largest GPU. This GPU is 2 petaflops, and the frame buffer is 512 gigabytes. For example, a reasonably high-performance gaming graphics card has 4 gigabytes of frame buffer. This GPU has 512. Incredible performance. The world's largest GPU, the fastest single-node computer the world has ever made. 2 teraflops in one node. One node basically means one operating system. Imagine if you have a data center of 300 servers, which this replaces with just this one node. Those 300 servers would have 300 operating system instances. This one node has one operating system instance. So imagine the reduction in overhead. Imagine how easy it is to program this computer. The world's largest GPU, the single fastest single node. Well, our GPUs, the Tensor Core GPU and DGX2, has achieved a whole bunch of speed records. We announced 5 speed records recently. Whoops. We announced 5 speed records recently. I'm going to come back to this. We have 5 speed records. The fastest single chip for deep learning, the fastest single node for deep learning, 15,000 images per second for training. Fastest at scale, it only took 14 minutes to train ResNet 50. Fastest inference, 1 millisecond. 1 millisecond. Imagine when you say, okay, Google or Siri, or you talk to the internet, you would like it to go to the internet, come back with an inference as fast as possible. 1 millisecond is our inference speed, the fastest in the world, and the highest inference throughput. So DGX2 as a computer has broken incredible speed records. Recently, we also took the DGX2 and the components inside. They made it available. For hyperscale data centers. Can you guys see this? This is, first of all, incredibly heavy. This is way heavier than that laptop. Yeah. This is 8 GPUs connected by a brand new switch. You see those switches down there? The 6 switches connect these 8 GPUs so that they can all communicate at the same time. Meanwhile, another card, another HGX2, could be overlaid on top of this one, and the switches can communicate with each other through these links. Okay? The world's fastest motherboard. Unbelievable. I'm holding on to 1 petaflops of computing. Basically, this is one of the world's fastest supercomputers for AI. Okay. So the HGX2, which is the component inside DGX2, is made available to all of the hyperscale data centers in the world. And so if you want to create a supercomputer in the cloud, all you have to do is standardize on this. This is a very important strategy for us and for the ecosystem here in Taiwan. This will do for hyperscale data centers what the ATX motherboard did 30 years ago in the PC industry. By standardizing on some basic architectures, it is possible to create hyperscale supercomputers incredibly fast of all kinds of different types of sizes. Does that make sense? Okay? So this is a hyperscale computing element. The HGX2. Oh! Wow! All right. We gotta keep it cranking. So that's HGX2, a computer for hyperscale computing, an industry standard, and has been adopted by all of the partners here in Asia. It adds to our growing list of server architectures. Now we have hyperscale. Now we have GPU servers of all kinds of shapes and sizes, starting with the HGX family, the T1 and the T2. T1 is based on DGX1. T2 is based on DGX2. Those are for training and for supercomputing. Then you have HGX I1 and I2 for inference. Inference is developing the software model. Inference runs the software models. And then we have supercomputing architectures called SCXE1, SEXE1, SEXE2, SEXE3, and SEXE4. Okay? And those are for high-performance computing and for deep learning. We now have architectures of all sizes and shapes for training, for inference, for supercomputing, for smart city, live video inferencing, for remote graphics, as well as for rendering. The number of applications for GPU servers is now really, really large. And we have all kinds of different configurations. Every single server company in Asia, the world leaders of server systems, the makers of 90% of the world's servers are here in Taiwan. And every one of them has supported and adopted NVIDIA's GPU architecture. I'm so incredibly proud and grateful for their support. From Quanta, the Foxconn, Inventec, Wistron, WeWen, Taiwan, Gigabyte, ASRock, Acer, and ASUS. Every one of the world's leading server makers are supporting NVIDIA's GPU servers. So, first part. The first part is about creating the processor, the system architecture, the tools, the software, the methodology, and deploying into the data centers all over the world. Job number one, the first phase of AI, to create the computers for developing the AI. To create the computers for developing the AI. Phase one. Phase two is developing the software for the various industries so that we can improve the velocity, the productivity, the amount of automation of each industry. We're focused on 6 large industries today for our GPU servers. And each one of them are going to be affected by AI. First, of course, is supercomputing. This is a $10 billion industry. Every server in the future will be GPU accelerated, will be accelerated of some kind. It's simply impossible to continue to extend computing forward without acceleration. AI, developing the architecture, as I mentioned, both for developing the software as well as deploying the software in the cloud for inference, transportation. For the very first time, we could develop software that could allow cars to perceive its surroundings and drive by itself. The driving car computer is one thing, but you have to develop the software in order for that car to drive by itself. The development of the software requires a supercomputer. The simulation of the software requires a supercomputer. And of course, the testing of the software against the billions and billions of miles that you'll have over time requires a supercomputer. We have a brand new platform called Clara. Clara is a computing system that looks like this, with a brand new software stack on top that does medical imaging, reconstruction, recognition, and visualization, the 3 fundamental areas of early detection. Reconstruction from raw sensor images of MRIs or CTs or ultrasounds or PET. Reconstruction, then detection, segmentation, identifying what are areas of concern and be able to automatically detect it, and then also visualize it. Another market we're focused on, a platform called Metropolis. Metropolis is a system software platform that allows billions of images from live videos to be able to come into a server and for us to be able to automatically recognize and detect areas of concern. And then lastly, we've been able to use artificial intelligence to even revolutionize the application that put us on the map. For the very longest time, it has been impossible for us to use our GPUs to create final film or photorealistic rendering. The images are too exquisite, and the algorithms are not conducive to GPU parallelization. It took us 10 years to develop the algorithm to do so. And after 10 years, recently at GTC we announced a brand new technology called the Nvidia RTX. And it merges 3 fundamental techniques. Next generation GPU real-time rasterization. Second, accelerated ray tracing. And then third, using artificial intelligence to complete the rendering. We were able to use artificial intelligence to accelerate ray tracing and pull in and make possible real-time ray tracing somewhere between 5 to 10 years earlier than we expected. And so today we'd like to show it to you. Guys? Everything you're about to see is completely in real time, and it runs on this particular machine right here. What you're about to see runs on
The
this.
story with all the elevators lately. I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hog. But you think she heard us? Yeah, I think she heard us. At least we blend in for once.
Can you guys imagine that? everything was done in real time. Now I'm going to show you real-time interactive ray tracing. Film quality, photorealistic rendering, and this is a level of imagery that simply wasn't possible without ray tracing. The soft shadows, the global illumination, the soft, where the ambient light is underexposed in certain creases, shows up as what is called ambient occlusion, which is really beautiful. You see the reflection of the light on his shoulder. You see the reflection of this stormtrooper on that stormtrooper. So the reflection, the shadows system is all completely automatic because we're doing this in ray tracing. Notice how beautiful the shadow is. This is called area lighting, which is incredibly difficult to do. Let's go, hey Jeffrey, let's go to the next scene. Let's go into the elevator. Could you imagine if a video game looks like this? This is going to be incredible. The Nvidia RTX technology. So now we're inside an elevator. Let's put Phasma in there. Phasma is really hard to do because she's completely shiny. And yet, her material, look at the reflection off of her suit. There's a sense of material on it instead of being perfectly smooth. Because even her outfit should have some warpage and some material feeling on top. Okay, let's move the elevator. Everything just lights up dynamically. All the shadows just work perfectly. Well, the future of computing is apparently going full speed, and there's a great deal of concern around the world. It's all your phones? What else could go? So first of all, I have to feed you guys. Now we have to evacuate the building? Is that right? Okay, calmly one row, please. Calmly. Phasma, could you just let's stop at the engine room. Let's take Phasma out into the hallway. So let's stop at the engine room. Open the door. Did you guys see the door open on her chest? Look at that. That's incredible. The benefit of ray tracing, and this is how film is made. As a light ray strikes a surface, it's either absorbed in the case of her cape, or it's reflected or refracted, depending on the translucency of an object. And the material surface is characterized physically so that something is shiny or something is rough, something could be bumpy, and everything just renders perfectly. Okay, so this is the future of computer graphics. It merges three fundamental methods of computer graphics. Our rasterization of our GPUs, programmable shading, which we invented about 15 years ago. The second is accelerated ray tracing. And the third is artificial intelligence or deep learning to accelerate the completion of the image. And by combining all of these three techniques, we're able to finally do real-time ray tracing for the very first time. This is running on 4 Volta GPUs. 4 Volta GPUs. And let's go to the next one. Okay, we're good. Thank you. Is it over? Are we safe? You guys know?
It's until 2.
Until 2? We're safe until 2.
Yes.
We're safe until 2. All right, so the first phase of AI is developing the fundamental computer. This computer is very different than the way computers are developed in the past. And this computer allows software to write software by itself. And the software that's written can do amazing things. The second phase is to be able to develop the software necessary to automate certain tasks or certain functions in these very large industries. whether it's in scientific computing to be able to finish complex simulations, merging high-performance computing methods and deep learning methods across all of these different industries. The productivity gains we'll be able to bring, the level of automation that we'll be able to bring into these vertical industries will really boost and stimulate these markets. So I'm quite excited about that. The second phase is applying the software to automate industries. The third phase is about the AI that's currently inside these computers to be able to come out of the computer into the world. However, in order for the AI to come out into the world, three things has to happen. Three things has to happen. We have to have rich sensors, because when something is inside the world, it has to recognize where it is, recognize and perceive its surroundings, reason about what it should do, and then, of course, act safely. And so, in order to do that, you need great sensors, rich sensors, whether it's cameras or LiDARs or ultrasonics or radars. It could be pressure sensors, it could be touch sensors, thermal sensors. The second thing you need is an AI brain that's really, really high performance, but very low power. And the third thing you need is smart actuators. And these electronic actuators are emerging everywhere. So the area where we can make a huge difference is creating a new type of brain. And if we could do so, we can enable billions of intelligent machines to be created. These intelligent machines will be able to do things in the real world that we do either mundanely or we don't like to do, or things that are very hard to do. And it can, of course, do it much more efficiently. It could be in delivery. As you know, more and more of us are just going to the web and ordering some food, and we expect the food to come to us. We used to go to the food. Now the food comes to us. And so we need a lot more people to deliver products to us. Industrial drones for delivery or for visual inspection, agriculture, to be able to do the meticulous tasks that are really requires articulation. And in all cases, as you can see, the data, the world is really unstructured. It's really, really messy information. There's no way for humans to write the software necessary for that to happen. Taken place, everything is all wiki-wonky and placed slightly differently in all these different types of bins and different products of different sizes. Logistics, different sizes of different products and different warehouses. It's impossible for us to program every single version of every warehouse and every product that we'll pick up. And manufacturing, of course, building things of different sizes and shapes. All of these types of activities, whether it's to do things that we don't want to do or do things that could be much more efficient or do things that are impossible for humans to do, requires, in the future, autonomous machines. We created a computer necessary to do that. At the core of that computer is a brand new type of processor. We call it Xavier. Xavier is the world's first processor designed for intelligent machines. It's the largest SoC the world's ever made. 9 billion transistors. It took thousands of engineers to complete. Inside this SoC, inside Xavier, are 6 different processors. 6 different processors. An 8-core high-performance full custom CPU, ARM CPU. It has a 512-core CUDA Volta Tensor Core GPU, 512 cores. It has a brand new programmable vision accelerator, a computer vision processor called PVA. It has a 1.5 gigapixels per second ISP, which basically equates to about 12 4K videos streaming into this one chip at one time. Imagine taking 12 4K videos and take the bit rate, the video, and run it into this processor, and we could process all the video at one time. ISP of incredible performance. We have a brand new DPU so that you could record and transmit video at very high rates. Everything is done in HDR, and there's a brand new deep learning accelerator we call the DLA. We now have 2 deep learning accelerators. One that's based on the Tensor Core GPU, and one that's basically essentially a TPU. The reason why we have 2 is because in many different applications, we need redundancy and diversity. We want to have the highest level of safety, and so by doing things two different ways and redundantly, we can ensure the highest level of functional safety, diversity and redundancy. So this is the Xavier. You know what? I forgot my transition. Let me do it again. You guys know that we've been working on self-driving cars for some time. The self-driving car was selected by us for the first intelligent machine, the first robotic machine to work on. And the reason for that is because it has a great deal of complexity, and if we were successful in doing so, the market impact would be great. An autonomous car, a self-driving car, has all of the same basic robotics functions that I'm going to talk to you about in all of the other applications. It has rich sensors. It has to figure out where it is, recognize its surroundings, reason about where to drive, predict where everything else is going to be in the near future, and then take appropriate action. That basic loop is the basic intelligent machines loop, the basic robotics loop. And so we decided to work on the self-driving car first. And the self-driving car has a whole lot of different types of versions. We have a version here for what is called a robot taxi. This computer here is the Drive Pegasus. The Drive Pegasus has 2 Volta GPUs that you see and 2 Xavier processors on it. Enormous amount of computation. 125 teraflops, and 30 each. So what is that? 250, 280. 280 teraflops of deep learning performance. This little supercomputer requires that much performance because the car has no driver inside. And we want to be able to perform many different types of algorithms all at the same time. This allows us to build essentially driverless taxis. In the future, we would also have cars that have a limited amount of autonomous driving. It won't be able to drive in every circumstance, but it will be able to drive in many circumstances by itself. And this is the Drive Xavier. This is the Xavier chip inside a self-driving car environment. Now I'm going to show you a video of all of the algorithms that are running on top of this Drive Xavier in order to create a self-driving car. All right, guys. Thank you. Network to recognize, to perceive, and to decide what to do. this, guys, working on self-driving cars it's just the greatest joy ever. And this car and all the software on top of it has to recognize, of course, other cars and lanes and signs and motorcycles and trucks and pedestrians and intersections and all that kind of stuff. It has to figure out where it is in the world, has to predict where the car is going to be, and has to find a path forward safely. And so this is such an incredibly fun thing to go do. Well, it turns out that the basic algorithms of perception, localization, and planning are exactly the same in just about all forms of robotics. And so today we're announcing a brand new computer we call the Jensen Xavier. Cheryl? All right, this little tiny computer is the world's first computer for intelligent machines. This little computer is going to be the brain of future robots. Robots that fly, that drive, that swim, that goes underground, that picks strawberries, picks lettuce, picks apples, that helps you in the lab, like Jarvis hands you your screwdriver. This little computer is the brains of future intelligent machines. We call it Jensen Xavier. 6 processors, 30 trillion operations per second, 12 nanometer FinFET, almost 8,000 people to design and develop the software for. This is the single largest processor project we have ever done in our company. It's taken several years. 5 years ago, we created specifications for it. It took 3 years to design, 2 years to architect. And today, Xavier production silicon is here. And we're announcing the world's first computer for intelligent machines, the Jensen Xavier. This will go into future robots. It comes in a module that looks like this. It's nice and beautiful. Okay, so this is the connector. This is an entire computer, and this plugs right into. I would not be surprised if the next time I saw you, I have one of these right here. Augmented human. The computer itself looks like this. Look at this computer. This is the development system. The entire computer. This has the processing performance of what used to be just recently a $10,000 high-end workstation with GPUs. Our highest performance GPU, the Titan XP, is barely faster than this. And this has 8 high-end ARM cores. A processor, dedicated computer vision, stereo computer vision. Incredible amounts of performance. And all in 30 watts. Essentially, a $10,000 workstation, 1,000 watts of performance, 1,000 watts of power, now fits in my hand for 30 watts. Incredible.
More energy.
I could hold this all day long. This I could do all day long. This I could do all day long. Here we go. You want this like this?
Yes.
This all day long.
Sexy, yeah.
Yes. Ladies and gentlemen, SCXB5. Sexy 5. That would have been a good name. Okay? All right, guys, thank you. So, Jensen Xavier. We're taking early access now. We'll be able to deliver early to the early access developers in August. We're building them as fast as we can now. And the dev kits are $1,299. what otherwise would have taken a $10,000 workstation to be able to achieve now is in one single processor, the world's first intelligent machine processor. There's the dev kit. Right. Here's the dev kit. And this is what it looks like inside. The extra review. $1,299 dev kit. The world's first intelligent machine. Fits perfectly inside autonomous machines. There you go. They're just getting smaller and smaller and smaller. It disappears in the phone. Okay, on top of this machine, just like we have for self-driving cars, we have all kinds of intelligent machine applications. And these are deep learning applications that takes advantage of all of the capabilities of Xavier. This is pose estimation. And the reason why you need to know is because depending on the pose of a person, you can predict what that person is likely to do, the direction that they're going, the action they're about to take. So you'd like to know, when you look at their pose, you can decide whether they're coming towards you or moving away from you. It's called pose estimation. We can use deep learning to infer that. The second is gesture recognition. Okay, so this is all happening in real time. All happening so fast, basically in real time. Video comes in and immediately you can see the pose. We want to be able to infer what is happening in the surroundings as fast as possible. This is face recognition and detection and tracking. So we can detect the face, but most importantly, we need to be able to track the individual. Where is that person going?
We're doing material science simulations. We have health researchers who are interested in modeling the heart.
And so in the future, we will do speech recognition on the device. And the reason why you want to do that is because of latency. When you're talking to somebody, you want them to hear you and recognize what you're saying instantaneously. You don't want it to go all the way to the cloud. What you want to do is recognize the speech, but go to the cloud for natural language understanding, and then come back to the device for speech synthesis. And as a result, speech will be very natural, it will be very fast. We want to be able to see where you're looking, and it has to be so accurate. And this is called gaze tracking. Where are you looking? Looking at somebody to see if they're making eye contact is very important in how we interact with intelligent machines. What is happening to the hand? Because maybe we want to use it for signing. Okay? Just go, hey, come over here. Because maybe that intelligent machine is quite far from you, and instead of yelling at them, you just go like this in the intelligent machine. Okay? You might be able to wave it off. No, it's okay, go back. All right? You want to know the depth of the environment. These are just some examples of computer vision algorithms. In this particular case, we're using deep learning to estimate the depth, the distance something is away from us. Okay? Otherwise, it's a two-dimensional image that comes into the camera. And then lastly, we want to know where are we in the world. It's called visual odometry. Just simply using cameras, we could infer where are we in the world and in what pose, what velocity and change we are relative to the environment. Jensen Xavier. All of the software that sits on top of it, the acceleration libraries, the SDKs, the frameworks for running the software, as well as the deep learning applications that are on top. But we don't want to test robots just randomly in the physical environment. The best way to test robots and to teach robots is to do it in virtual reality. And so we created a simulator, a photorealistic simulator that runs on a GPU server. We call it Isaac Sim. The simulation environment basically simulates the world, takes the world information, and emulates the sensor, sends the information to Jensen Xavier. The Jensen Xavier runs the software and sends the control back to the simulator. And inside the simulator, the robot is moving. We will teach the robot how to be a robot inside this virtual reality world we call Isaac Sim. And when we are done, we take the software and the computer and we put it right into the robot. And it should just work. It should just work. Okay? And so this is the way you're going to create robots, because otherwise it will bump into things and hurt people and break things. We could let it try to be a robot inside a virtual reality simulator, develop all of our artificial intelligence software and applications running on this computer. And it basically is exactly the same computer. This is called hardware in the loop. Hardware in the loop. This is hardware. It's inside the loop of the control. What it sees, what it controls, what it sees, what it controls. As you know, as I've said already, robotics has three fundamental jobs. One, perception. Perception of the sensor. Two, the brain. And three, the actuators. 1, 2, 3. The fundamental computation loop of a robot. And when we're done with the software, we can put it right on. Isaac is going to be the third phase of the AI revolution. First phase is developing the software and the computing architecture and all the software on top. And the second is to apply the software to automate large industries, drive more productivity. And third, the AI is going to come into the world in what we call intelligent machines, largely called robotics. The development of these robots is happening all over the world already in little tiny versions of Jensen today. And let me show you some of the applications. It's really amazing. imagine now we have Jetson Xavier. That's with Jetson TX2. And that's what we're able to achieve. That's what we're able to achieve with last generation Jetson. And now we have something that's over 20 times more powerful. Imagine what you're going to be able to do. All the different types of sensors, the articulation, the speed that it will think and be able to interact with us. The age of intelligent machines has arrived. Today, we're announcing that we have a long-term collaboration with Taiwan, with MOST, which is the Ministry of Science and Technology. Taiwan's industry and its research education and all of the scientists in Taiwan, as much as anybody else, would love to be able to enter the world of AI and to be able to accelerate the development of AI here in this nation. The applications, whether it's to advance research, scientific discovery, as well as to advance the industry, is obviously incredibly important. We today announced a collaboration, a 10-year collaboration that we're going to work with the industry, the research institutions, and the government to advance AI here in Taiwan. It starts with building a supercomputing infrastructure right here in Taiwan. Most announced that we're working together to build a very, very fast supercomputer that's dedicated to AI research. See, it's such great news. It's red alert somewhere. We're going to work on a supercomputing infrastructure to advance AI discovery and research. We're also going to work on self-driving car platforms and discoveries and groundbreaking work in that area, as well as working on intelligent machines. So today we announced our collaboration. I'm super excited about it. So let me quickly summarize.
32 o'clock over.
You're right. It's lunchtime. There's a lot of activity today. Okay, so we talked about 4 things. The first thing is the driving force of gaming, the driving force of our GPU technology, GeForce. The PC gaming market is super vibrant. The invention of Max-Q has made it possible for us to take the highest end GPU capability, gaming capability, into the thinnest of notebooks. And so now you could have a wonderful gaming platform as well as a beautiful notebook. And this could be your favorite notebook, your favorite gaming platform. You could game wherever you like. We also talked about the importance of the continuing improvement in content quality that's driving the adoption of higher-end GPUs. Has grown 3x in 5 years. 3x in 5 years. And also PUBG and Fortnite, a brand new genre that's driving the gamers into the marketplace. In just the last 8 months, we've seen 10 million new GeForce gamers. It's a new era in computing, and we're talking about AI, and it starts with creating the fundamental computing architecture first. Then using that architecture to develop new types of software that could create automation for all the different vertical industries. And then lastly, taking the AI out of the cloud, getting it from the data center, and putting it into an autonomous machine, which required us to create Jensen Xavier, which is our first intelligent machine processor, as well as the Isaac machine stack for intelligent machines. First, we had to hunt for sandwiches. We had to raid the mini bars for cookies. And now we have emergency sirens. The best press conference ever. Okay, guys, let's. Can I answer your question? Who has a question? I understand that microphones are all around us, and that I'm trying to yell, and it actually does take the wind out of me. Now, do they have to do the same? Okay. Anybody who has a question, just yell. Yes, yell, sir.
So is the Jensen Xavier using the same Xavier SoC as the drive Xavier?
Yes.
Exactly the same.
It's exactly the same processor that is in here. That is in here. The same this is the beautiful thing. This architecture and this architecture and this architecture and this architecture is the same. And that's why software that's written by this computer will just run on this computer. Does that make sense? The software that is written by this computer will just run naturally on this computer. And the algorithms for perception and localization and planning are very similar between a self-driving car that has to move at 75 miles an hour with everything moving around it versus a robot that has to move at 1 meter per second. Does that make sense? And so the amount of processing that is required for a robot is surely less than a car with all the sensors around it traveling at 75 miles an hour. But the basic algorithms are very similar.
When drive system outputs multiple GPUs, but they said it's got multiple GPUs. Has that changed, or is there a second generation coming?
There's a second generation coming because there's these adapters.
Yeah.
And all you have to do is pull this out, and then someday put another one in. And that day will happen on the day that we have another party. And I want to invite you for sure. Okay, and that's the beautiful thing, because they're all software compatible. I could take this module out, put a new module in, and it just works. That's the beautiful thing. A thoughtful computer architecture. Okay, one architecture. Anybody? But you have to allow. Yes, sir.
You play Fortnite or PUBG? Which one's better?
They're both great. PUBG, Fortnite, they're both amazing. Next. All I know is that in 8 months, 10 million more gamers came into the marketplace. That's extraordinary. Yes, sir.
And PC gamers are seeing this new Volta architecture, this exciting architecture in all kinds of markets, data center, AI, self-driving cars. They can't wait to get it themselves for gaming. Have you anything to say to that?
Well, what I have to say is that first of all, as you know, there are so many gamers in the world who were deprived of GeForces in the last several months because mining drove demand so high. Finally, I'm so relieved that the pricing of GeForce cards are coming down. And so 1080 Ti's and 1080s and 1070s, they're the best graphics cards in the world for gaming. They're going into PCs, as you know. They're going into these wonderful Max-Q notebooks. And so I would go out and buy a GeForce ASAP. That's what I would tell you. It's back in the marketplace. Yes, sir.
Are you measuring those 10 million more games? Is that just total GPUs sold, or would that be like unit installs, like Fortnite and PUBG, like running Nvidia GPUs?
We monitor the number of active GeForce gamers on a weekly basis. Active GeForce gamers, whether they're playing, whatever game they're playing. In the last 8 months, the number of active GeForce gamers literally increased 10 million people. Some of them are probably new gamers. Some of them could be somebody who hasn't been playing games for a long time that came back into games.
So
Active GeForce gamers. Probably a lot of them are new gamers. Yes, of course. NVLink is a really important technology. It's absolutely right. And it connects NVLink connects every GPU to every GPU, and it comes through the switch. So every GPU goes into the switch, every single GPU goes into the switch, and every switch is connected to each other. Now everybody can talk to each other at the same time. Now this is only on one node. However, we have the ability to extend it beyond the node. And it looks like this. This is the backplane. And so as a result, different nodes can be connected in this high speed, 300 gigabytes per second. per GPU. Unbelievable. And so we literally take this back plane, we stick it between the motherboards, and we clamp it together. Well, over time, you can. Yeah, it's really good. Yeah. Let me take a question back there. Anyone? I'll come back. If you ask another question, there's other stuff back here. Yes, ma'am.
Well, my first question is what's behind there? My question is about the future of autonomous machines and intelligent machines. How long do you think it is timeline-wise until we start to see these become really commonplace? Kind of crystal ball for us, and what excites you most about this?
Yeah, so regarding autonomous machines and these intelligent machines, my single favorite is actually the self-driving car. And the reason for that, the reason why we worked on self-driving cars first is because the impact to society is enormous. You know, obviously a lot of people get hurt driving cars. And here we are driving and we lose attention, or you know, something happens by accident, and it's beyond our capability to maneuver properly. And so these cars are always going to be paying attention. They'll keep us out of harm's way. They'll be able to move products much more cost effectively than we could do today, which will reduce the cost of products, increase demand, increase quality of living, right? And so that's going to be great for society. And so in the future, what's going to be super exciting to me is that reducing the cost of insurance, reducing the cost of injury and damages, decreasing the cost of delivery of goods, which increases its consumption and quality of life, is going to go up. I think that self-driving cars will unquestionably be one of the most powerful driving forces of the economy going forward. Trucks, shuttles, trains, planes, automobiles, it's going to be autonomous machines, everything. Yes, sir.
So AI accelerated ray tracing. Fabulous technology. It's probably where ray tracing is going, but currently you need a system for massive GPUs to get it to run. Should we expect it in gaming in the next GPU generation, or is it still going to be further out?
Yeah, so deep learning accelerated ray tracing. You guys saw the visual quality. It's really quite amazing. Reflections, refractions. It took this machine. It took this machine to do it in real time. And so this has 4 Volta GPUs inside. And so this young man's question is can we imagine that this would someday be in a consumer graphics card? And the answer is of course. The question is how long. It takes quite a long time to shrink this particular machine, which is $68,000, okay, $68,000, into a graphics card that goes into that laptop. And so that's going to take some time. I think that the exciting thing for us today is that because of RTX, because of Nvidia RTX, now game developers, filmmakers, could now have the benefit of GPU accelerated ray tracing, and it accelerates their content creation and reduces its cost. And so we're just seeing incredibly great excitement around RTX. I think every film studio, every game developer will use, every architect, every car designer will use RTX to be able to produce those images much, much more quickly and cost effectively. And then someday, we would love to be able to bring it to the mass market.
Are any games that are actually challenging limits for the Nvidia GPUs at the moment? Because what you're announcing is mobile, but it seems like your best graphics cards are already way too powerful for game applications nowadays.
Yeah, so the question is, are there games that challenge our graphics cards? The answer is a whole bunch. And the reason for that is because we want to run these games at 4K resolution, anti-aliased, with all of the settings turned on, all the particle physics simulations turned on, and to run it at 120 hertz. And quite frankly, what I just described is not possible for any of our high-end graphics cards today. And so we're continuing to push the limit because of that very reason. We would like, watching a movie is a passive experience, so 30 frames per second looks just fine. But when you're playing a video game, 30 frames per second is actually terrible. And so you really want the frame rates to be high. so that the latency is low, so that everything's nice and silky smooth.
Just follow up to that question. So, can you give us a hint when we might be able to run 4K? What do you hear about the single part? Say a day, an hour.
4K, that's something I don't know how to predict. That's beyond my limits. No, not really. I can predict it. I won't. Because I want to, you know, I like you guys. I want to spend time with you guys. So we can't talk about everything in one shot. Today we talked about Max Q. We talked about AI. We talked about all of the markets that it's going to go and automate. And we talked about intelligent machines. We talked about so much. The question is, do we have plans to come up with mining-only cards? We have mining-only cards. We try to create mining-only cards to take, to diffuse the demand, to reduce the demand in the marketplace, the open market for GeForce. The reason for that is because we created GeForce for gamers. And the last 6 months, the demand was so high that it was so hard for a gamer. I get so many letters from, you know, from people that or fathers and guys that, you know, people that just want to buy a gaming card and they couldn't. They just get everything sold out. And so, you know, mining is a bonus to our business, but it's not our business. We have so much growth in all of our businesses. I would rather that mining demand subsides a little bit and allows the GeForce cards to be out in the market. And so we did create a mining specialty SKU. We call it CMP, and we sold it directly to miners. Hopefully, their needs could be subsided that way, and then I saved the GeForce cards for miners. When's the next GeForce? The next, I'm going to invite you guys. Don't worry. I promise. You know, you guys. Not only will you be invited, you know, there'll probably be lunch. There was a question back there. I won't forget you. I promise.
How'd you give us
A little hint? It's a long time from now. It's a long time from now. Yes, sir.
When you present exhibit for autonomous driving, you showcase your own car as well. So right now the question is, do you have a robotic program? I mean, hardware robotic program.
Yeah, so in the case of the self-driving car, the reason why we had to go build our own self-driving car is because 7 years ago when we started working on this, there were nobody working on it. And how would I know what processor to design if I didn't understand the algorithms on top? And so we decided to work on the algorithms on top. And as we're developing the algorithms on top and trying to figure out what kind of computing is necessary, computing style and computing load is necessary, we could design the processor at the same time. And so you might have seen, this is called the Drive Pegasus. The last generation is called Drive PX2. Drive PX2 was our development system for all of our autonomous vehicles. It has been shrunk into this. So this, what used to be this, looks like this, is now Drive Xavier. That's how I knew how much computing is necessary for Drive Xavier. Now in the case of robotics, we're building our own robot. It's a little tiny platform, it's called Carter. And you saw it has 2 big wheels, has LiDAR and camera and ultrasonics. And we develop all of the necessary algorithm. And then we open the platform for people. They could use all of our AI networks if they like. They could create their own if they like. And so, you know, we want to create an open platform that inspires people to make these intelligent machines as easily as possible. Okay, so we solve both of it at the same time. Yes, sir. I saw a question earlier. Yes, sir.
It was recently announced at the Computex conference that Nvidia would have a 12,000 next-gen GPU, and that suddenly changed to
You have got to live in the present. Come back. Come back.
I'm just wondering if the talk is still going ahead.
I promise to invite you. You know, we have parties, so many parties. Yes.
Just on the mining question,
yes.
Does it like personally annoy you when you create these powerful machines to enable all these amazing gaming developments and people speaking in the back shed?
it doesn't annoy me. The reason why you guys know this. You guys know that GeForce is the world's largest distributed supercomputing platform. The reason why cryptocurrencies want to run on these large distributed systems is so that no entity has control over manipulating the currency. That's the reason why it wants to be distributed. And so in the beginning, many currencies will start out being GPUs. Sometimes a few of the currencies are easy to turn into an ASIC, and then the power centralizes into a couple of companies. The community doesn't like that, creates a new algorithm, distributes it back all over the world. Okay, so there's a reason why our GPUs are perfect for cryptocurrency. And so we understand that. And I love the idea of blockchain. I love the idea of distributed ledgers. I love the idea of cryptographically, protected file systems. I love all that. And so I encourage that. However, we have to stay agile so that whenever the mining demand comes, we could fulfill it somehow and then continue to allow the demand for gamers. So I'm not annoyed. It's a bonus in our business. I don't count on it. It's a bit of a bonus. But right now I'm just super delighted that the price of GeForce cards are back down. Yes, sir.
Hi, we're seeing, I think, more of a union between CPU and GPU computing from your competitor.
We don't unionize.
Yeah, well, I mean like the CPU and the GPU all in one, all in one as one thing.
Union.
I'm wondering, where does that leave Nvidia? Because it does seem like you're focusing on GPU computing.
Yeah.
But if Intel can bring in GPU graphics,
yeah,
it seems like strong competition for you.
Yeah, there are places where integration is really great. For example, this is great integration. This has 6 different processors, not 2. A CPU and a GPU is not enough. You need a computer vision processor. You need sensors, processors. You need you need all kinds of different types of processors. On the other hand, this computer hates integration. This computer hates integration. This computer wants to be disintegrated. And the reason for that is because sometimes you want 1 CPU per GPU, sometimes you want 1 CPU for 2 GPUs, sometimes you want 1 CPU for 8 GPUs. And so the configuration, the amount of salt and pepper in that dish is separate. If you created a spice that is salt and pepper combined, unified, a unified salt and pepper, it's less useful than salt and pepper. It just depends. I just used a metaphor that I'm going to regret.
I was saying, what about 5 Spice?
5 Spice. Well, 5 Spice is very special.
Yes.
Yes.